chemical Bronsted-Lowry theory, which applies a broader range of chemical reactions. So, ang target po natin ngayon ay ma-define kung ano nga ba ang Bronsted acids and bases, discuss the acid-base property of water, and calculate pH from the concentration of hydrogen ion and hydroxide ions in aqueous solutions. So, familiar ba kayo sa word na pH? Narinig naman yun. At familiar din kayo sa term na acid at base. Tama? So, medyo madali lang siya itinuturo. Okay, kung mababasa niyo dito, nagkaroon lang siya ng brief na discussion sa history. No? Sa 1923, yung chemist daw na si Johann Nicholas Bronsted at si Thomas Martin Lowry ay, sabi, independently developed definitions of acids and bases based on the compound's abilities to either donate or accept protons. Ibig sabihin, yung ginawa nila na basihan sa pagbibigay ng definition sa acid at bases ay tungkol daw dun sa ability. Okay, yun lang muna yung pinagbasihan nila. Yung ability na makapag-donate at makapag-accept ng protons. Ibig sabihin, ang i-discuss lang natin ngayon para mag-define kung ano yung Bronsted-Lowry acid at base ay nakadepende sa pag-donate at pag-accept ng protons. Okay? Dito nila sa first paragraph pa lang, alam na natin kung ano yung scope ng ating lesson ngayong araw. Okay? Tapos kung makikita nyo dyan, i-define lang siya, no? At nagbigay lang siya ng example. Ang example natin na binigyan agad kayo ng chemical equation. Okay? Makikita nyo dyan, HCl plus NH3. Tapos nag-turn siya into NH4 plus Cl minus. Kung makikita natin, balance na yung equation, tama? Bibilangin natin yung nasa kabilang side. Ililista muna natin. Para malaman natin na balance. Alam ko naman mga space pa kayo dyan, kaya kailangan na natin i-review. Formula ay equation na lang HCl. Alam niyo na naman yan, HU aqueous plus NH3. Kung paano natin malalaman na balance na yung equation natin, titignan muna natin dito sa kabilang side. Ito yung ating mga reactants. Ito ang ating product. Diba? So, ito, meron tayong isang H. Tayo pala apat. Isa, tapos tatlo. Tatlo. Tapos meron tayo isang Cl at meron tayong isang N. Dito, ang H natin, kitang-kita, apat. Tapos, isang Cl na pala. Cl, isa din. Hindi na natin i-consider. Ito naman ay ano lang para i-define niya lang kung siya ay cation or anion, di ba? Yun yung purpose ng mga charges natin. Tapos, yung N naman ay isa din. Makita lang, 411, 411. Okay, so balance ang equation natin. Kasi, higit sa lahat, bago ka mag-start ng mga ganyan na computations, kailangan balance mo na yung equation natin. And then, anong sabi? Here, hydrochloric acid or HCl donates proton to ammonia, which accepts it, forming a positively charged ammonium ion and a negatively charged chloride ion. Therefore, HCl is Bronsted-Lowry acid, which donates a proton. Ulit. Makikita natin dito, ulitin natin yung kasi minsan, yan pag binasa natin, hindi agad natin mabigets, no? Kailangan po ulitin natin. Pero kailangan kasi muna, ma-define natin kung ano yung Bronsted-Lowry acid at Bronsted lauric base. Nakalagay kasi dito, a Bronsted lauric acid is a proton donor. Kasi yung pag-donor, sa dugo, mag-donate ka, donor ka. Ibig sabihin, maglalabas ka or magbibigay ka ng dugo. So kapag sinabi na Bronsted lauric acid, yun ay nag-donate daw ng proton. Ano ang proton natin? Negative discharge or positive discharge? Positive discharge. Tapos, kapag naman daw tinawag natin na Bronsted lauric base, yun daw ay proton acceptor. Okay? Nag-a-accept naman siya ng proton. Ngayon, dito sa equation na to, alin daw dyan ang Bronsted lauric acid at Bronsted lauric base. I-determine natin. So, yan sa example, anong sabi? Yung hydrochloric acid nakalagay here, hydrochloric acid donates a proton to ammonia. Ito muna. Ang ating hydrochloric acid ay HCl. Ito yun, hindi yung proton. And then, sabi, nag-donate daw siya ng proton sa ammonia. Ito yung ammonia natin. Saan natin nakita na nag-donate siya? Kita. Ang ano pala natin, ang dinodonate natin, dahil nga proton ang dinodonate, H plus ang kinuhanan natin. Diba? Ito yung dinodonate natin. So makikita natin sa HCl, meron siyang isang H na pwedeng i-donate. Ngayon, dito daw siya nag-donate. Saan natin makikita yung product? Ito siya. Tama? Nag-donate siya ng isa na H, napunta dito, naging NH4, ito, dahil nabawasan ng isang H, ito na lang siya. Okay? Very simple lang nung equation. Isa kasi, pag nakita na tayo ng equation, yan, ulit. No? Pero, kapag inintindi nyo mabuti, dahil meron namang description or merong explanation sa ilalim, makikita nyo, yun pala yung nangyari. Ngayon, nung nabawasan na to, ng positive discharge, anong nangyari din sa chloride? Ay sa, tama. Siya ay naging negative discharge. Okay? Negative discharge, chloride. Okay? Ngayon, i-determine natin kung ano na tayong Bronsted lauric acid at base. Ano ulit ang definition natin? Kapag nagbibigay, siya ay acid. Kapag tumatanggap, siya ay base. Pero yun ay Bronsted lauric na yung ang niya, kasama niya kasi meron tayong Arrhenius base at meron din tayong Arrhenius acid. Isa lang ano ko? Ito ang nag-donate, tama? So, ito ang ititrip natin as Bronsted. Direct ko na lang ka, Bl acid. Okay? Tapos, ito naman, dahil siya yung tumanggap, siya yung Bl. Ngayon, ito, na-form into this. Kapag nanood kayo ng videos, yung mapapanood yung videos mamaya, ito lang din yung i-explain na. Para mapadali lang yung inyong understanding. Kung ito acid, ano ang kapartner nito? Yung HCl, ano ang kapartner nito dito sa kabilang side? Diba? Ito siya. From base, HCl, naging ganito na lang siya. So, kapag ito daw ang tinrate mo as Bronsted lauric acid, ito, i-label mo siya na base. Pero, siya ay conjugate. Mamaya malalaman nyo, ha? Kung ano yung ibig sabihin ng term na conjugate. Tapos, kung ito naman yung ginawa base, dahil nga, ang pinagbasahan naman natin ang pag-determine dito sa dalawa ay kung sino yung nagbigay at kung sino yung tumanggap. Tapos, saka na lang natin siya nirelate doon sa product na form. Kapag ito yung acid, kung ano yung kapares niya dito, yun yung kabaligtad, acid, base. Kapag ito base, ito namang kabila ay acid, pero conjugate. Okay? Yun lang po yan, ha? Now, the ammonia or NH3, siya lang daw yung Bronsted-Lowry base which accepts the proton. Also, Cl negative is called conjugate base, Cl conjugate base, at NH4 conjugate acid. In this theory, or yung Bronsted-Lowry ka, ay sinasabi ang acid is a substance that can release a proton, ulit-ulit na naman, no? Like in the Arrhenius theory. Base is a substance that can accept a proton, inulit na naman. Okay? Tapos, hindi ba natin makikita yung definition ng bawal? Okay. Mamaya yun pala sa video. Okay? So, proceed na muna tayo sa acid-base property ng water. Ano kaya ang meron na mga interesting part sa water? Kung bakit isama na naman siya. Diba natatandaan niyo, meron tayong freezing point elevation at yung boiling point depression. No, meron tayong ganon. Sa water pa rin yun, di ba? Water pa rin yung diniscuss natin. Ano naman kaya ang meron sa water? Ang sabi is an interesting compound in many respects. Here, we will consider its ability to behave as an acid or base. In some circumstances, a water molecule will accept a proton and thus act as a Bronsted-Lowry base. Meron na tayo isang example. Meron tayong HCl plus H2O. Hindi ko na nalagay yung mga label na ano, ha? L, AQ, under H3O plus L. Ayan. Meron na naman tayong mga equation. Ano daw ang interesting part sa water? Dito sa formula na to, ang nangyari, ito ay nag-donate ng isa dito. Kasi meron na form ka ng H3O. Tama? Yung H na naman ito, nakula dito, napunta dito. Nag-donate siya. Ito, napunta doon. Kaya naging H3O. And then, dahil nawala na naman nga siya ng H, yung Cl na tira, nandun na naman sa makula. Okay? So ngayon, kung ito ay nag-donate, ang donor natin ay lagi acid, at nag-accept itong water, ibig sabihin, ito yung Bl base. Okay? Kaya makikita niyo po dun sa explanation, malagay ko. Ito yung circumstance na naging Bronsted-Lowry base ng water. Kasi nga nag-accept siya. Tapos, dito naman sa isang equation, ano nangyari? Yung H2O plus NH2 negative OH yan. So, ano naman nangyari dito? So, H2O, kanina ito ay Bronsted-Lowry base. H2O. Ito naman, sa case na to, H2O, dalawa ang H niya, nag-donate siya ng isang H dito to form NH3. Tapos, yung H2O, dahil nabawasan ng isa na H, magiging OH na lang. Ito siya. Okay? Tapos, kung ang H2O ay, ano nangyari sa kanya? Nag-donate. Tama, nagbigay siya ng isa, kaya naging OH na lang siya. Magiging Bl acid ang H2O. Okay?
you. What are Bronsted-Lowry acids and bases, as well as conjugate acid-base pairs? In this video, I will go through 5 examples with you. We'll work them together, and we'll label the conjugate acid-base pairs. As well as, we're going to add in the concept of chemical theory, also called chemical. Alright, before we can work those examples together, let's go through the definitions so we can label the conjugate acid-base pairs correctly. A Bronsted-Lowry acid is a substance that can donate a hydrogen ion, also called a proton, and it'll be a reactant in a reaction. On the product side of that reaction, it will have a pair called a conjugate base. It will differ by one proton or one hydrogen ion, same thing. Alright, next, what's a Bronsted-Lowry base? What's a substance that can accept a hydrogen ion, also called a proton? And it'll be a reactant in a reaction. And then on the product side, it will have a pair called a conjugate acid. That again will be different by just one hydrogen ion. Alright, so let's get started with our first of the 5 examples. Alright, here we go. I actually have a pen ready a little bit here. So here there are 2 substances, and what we're going to do is we're going to write them down, and we'll label them as an acid or a base. Okay? So this is HCl. I'm not going to worry about the state of matter. And this is water, H2O. And this is a strong, we'll say acid or base, so it dissociates completely. And in a separate video, I will go over strong acids and bases and how to calculate their pH. You can check that out. And what's going to happen is the chloride ion will be 100% dissociated, and we will have the hydronium ion also. So let me just model that with our models here, then we'll label these. So this is going to be the product. Hopefully we'll stay the hooks to kind of roll off the table. And this is going to be a product. Right? Let me just grab in another set to label them so you can see which one is differing by a proton. Well, they both are, but how they're differing by a proton. So kind of think when you label which one is the acid or the base. Remember, Bronsted-Lowry acids donate a hydrogen ion, and Bronsted-Lowry bases accept a hydrogen ion. Alright, here we go. So this is hydrochloric acid. You've already recognized that. It is a strong acid, which will be able to dissociate completely 100%. Water will act as the base. And on the other side, remember, the acid's partner is a conjugate base, and the base has a partner called a conjugate acid. Now, I'd like you to do is also get used to just listing these like almost like a sentence a little bit. So you'd say HCl has a partner called, or the pair, I just call it a partner, has the chloride as its conjugate base pair to its acid, and our H2O is going to have a partner called, or a pair called the hydronium ion. So it's called a pair. I keep calling it a partner, but I think of it like that. So they're different by one proton. Let's kind of show we're one hydrogen ion with the models. So do you see how this is differing by one hydrogen ion? Alright, so that's why that's one of the pairs. And then this is the acid, this is the base. And then take a look at these. Again, you see how they're differing by, here's my water, here's my hydronium, how they're differing by one hydrogen ion. I wanted the models to be really important for us to get really good at this, okay? So there's our first set, okay? We're going to switch this out, and I'm going to keep water, actually, and I'll keep the pluses and stuff. But we're going to switch this out with ammonia. So here's what it looks like on the model kit. And we're going to keep water. I'm just going to use a little different model kit here this time. Check 3 different ones we're going to use. So take a look. Let me write that down. I'll take these away because I didn't say what's what yet. So this is ammonia. Again, I'm not going to worry about states of matter. It is a weak strong, or weak versus a strong. So it is a weak acid or base. So it's going to have what's called a double arrow reaching chemical equilibrium, which I have a video on if you've never heard of chemical equilibrium. And on the product side, it's going to have ammonium ion and hydroxide ion. Make sure you have those charges so that the reaction is neutral on both sides for this one. Okay? So let me model it first. So what's going to happen is this water molecule here is going to have the hydrogen ion be protonated onto the ammonia. We grab these to look at to start with. Okay? So I think it's nice to look at the partnership. So keep behind you, label them. This is going to act as an acid this time, the water is, and the ammonia is going to act as a weak base because it reaches chemical equilibrium. That also means it makes only partially ions or partially dissociates or ionizes. Remember, the base has a pair that will be an acid, so the ammonium is ion is going to be the conjugate acid, and the conjugate base is going to be our hydroxide. All right? So let's list these again. So our NH3, its pair is NH4 1+, so this is the base, this is the conjugate acid. And our water is going to have a pair, it's going to be the, oops, sorry, not the hydrogen ion. It will be paired with the hydroxide ion. Okay? So again, this is acting as an acid, so it will have a conjugate base as a pair. So again, let's look at those one more time. Here's our ammonia. Model is super helpful, I think. You can see again that one proton difference, and then here's my water, and here's my hydroxide ion. Okay. It's also what makes this act as a base is that we make hydroxide. And that's again in another video. All right. So let me see. I'm going to see if I can erase these and start again. The only difference this time is we are going to do kind of like a neutralization reaction or an acid-base reaction. Not with water though, okay? So I'm going to keep it's all kind of a mess. Keep that. I'm going to add it with the HCl. So let's try this, and it is going to be a chemical reaction. So we grab these. I have another model kit. I don't really have a model kit. You have. I have a lot, okay? So then there's my HCl. It has a tendency to roll off the table. Let me tell you what the products are. So we will make chloride ions, and we will make ammonia. A little different than a lot of acid-base reactions that produce water. This one actually does not produce water. So let's kind of look at the modeling here. So here's my chloride. It's going to keep that lone pair. That's why I kind of have the line here to show you that that's negative. And this had a lone pair that accepted the proton and we placed it on top of that to make ammonium. All right, so let's get the other ones in here. So you gotta take a look at them. Remember, the reactants are the ones that make the products. Okay, so then let's label these. I think you already knew that it's the base and this is the acid, but remember to label your proper pairs. So my acid, I kind of put these out of order, and that's okay. So maybe you would have preferred I switch these two. It's fine, okay? You can do that if you'd like. But you might not see that. So this is going to have the conjugate base ion is the chloride, and the acid. Another thing that's kind of nice about that is it's base acid, base acid. So just be okay with that. You can have the products flipped in different spots. All right, so let's list the pairs. List the pairs. Ammonia is the base with ammonium ions. That's the base, this is the acid. And we have our HCl paired with our chloride ions. Again, let's take a look one more time. What do they look like? So here's our NH3, here's our NH4 plus, which is ammonium. And there you can see there's one proton difference. And here's our HCl and our Cl, one hydrogen ion, which again, proton and the hydrogen are the same. Talk about that in my KW video, my auto ionization of water. All right, last but not least, I'm actually going to switch to a different color. We're going to do kind of a unique one here. And what I'm going to do is, I don't know if you noticed, but water, when we did react with water, it could act as an acid or base. Let me bring in this term, plus this ion I have right here, has the possibility to act amphoteric also. Really, water is our main one, but we could have other substances be amphoteric. So I'm going to write that definition down. Here is right here. And what this molecule, or is a molecule kind of an ion, in my opinion, you got this bicarbonate ion, okay? And I'm going to put it back with water. And water is one of the classic amphoteric substances. But let's do the easy one to model first. This is going to be kind of a weak acid or base reaction, so it'll have what's called equilibrium and it'll have a double arrow. Let's have the easy one to model is what if this turns into H2Cl3? That would be one proton different, and then hydroxide. Okay, so think about what that would be labeled as. So let me show you what that would be. So if this is going to turn into hydroxide, I'm just going to have an open dot there. Plus, I want this to not roll off the table, so it should stay. Here we go. And so there is like a lone pair here. It's a negative charge on there that we can have. Notice on this side, We have -1, and this side we also have -1, so the charge has to be conserved. And then that's called carbonic acid. I'm going to pull this definition off, I'll bring it back. But let's label them, so here they are again. Here we go, almost to the end, though. This is our fourth example. So we've got our water is donating a hydrogen ion, so it's acting as an acid this time. And that means the base is going to accept a hydrogen ion. So now, oops, sorry, not that one, this one is the base. You're like, yeah, that's wrong. The base should be that one. And then on this side, remember the base has a conjugate acid. As I said, that was carbonic acid. It's a dichroic acid, which we had in another video. And then there's our conjugate base. So let's just kind of list what the shape this looks like. Okay, nice and dark. So you got HCO3 with H2CO3. Again, look how there's one proton and one hydrogen ion different, and then H2O is paired with hydroxide. This is our acid, this is our base. This is our ion. This is our base. This is our acid, conjugate acid. Okay? We grab those one more time. Here's my base. Here's the conjugate acid. And then here is the water, and here is its conjugate base. Okay. Now let's go back to this one. Start here. What if this acted the opposite? Okay? So what if it acted the opposite way? So let's switch this up. Because bicarbonate could be antibacterial, so let's just get rid of these. Okay? Think about what you'd write if it did the other way. So what if it acted as the acid and water acted as the base? And this will get to like K values later, Ka and Kb. And we can prove which way bicarbonate kind of prefers to react with water. But for now, let's look at the possibilities. So that means we're going to have the CO3 minus sign called carbonate. And then we'll make, this is in the frame, okay? They make H2O plus, which is hydronium again. Alright, so that means if that's the acid, it's got a conjugate base of the bicarbonate and the carbonate. And then the water will have a conjugate acid with the hydronium ion. So then I'll hold those up and have it react. So what if this donated? Now this is a hard one to model. Because you can't, there's these molecules don't let me make it look a little bit like hydronium. So there's our hydronium. It's actually not trigonal, planar though it is trigonal here. I don't think that's fun. Just kind of tip it up like that. Let me bring in the originals here. Here's our bicarbonate ion, and here's our water. And I actually have videos on how to do dot structures for these, if you'd like to look at that too. Or dot structures for lots of carbons. Alright, so there's our conjugate acid base pairs. We hold them up. We've got our bicarbonate and our carbonate. And we've got our water and our hydrogen. There it is, okay? And again, different by one proton. Alright, so I hope this helped. Let's bring these definitions all back out again and list them for you that in case you may be like, you know what, I should wrote those down. I think you're right. So here we go. Here's our Bronsted-Lowry acid. Here's our Bronsted-Lowry base. Let's get these off of here. It's not going to be perfectly erased, but that's fine. We have acid always pairing up on the other side as a product with a base. And we have a base always pairing up with an acid, conjugate acid on the reactant, the product side. This is the reactant, this is the product side. And there is a possibility you get water being really commonly amphoteric, but there are other substances that can be amphoteric. Alright, I hope this video helped you chemists understand how to label your conjugate acid base pairs. I went through 5 examples, hopefully have this squared away. If you need other help on acids and bases, pH calculations, or you deciding if it's a strong acid or a strong base, or a weak acid, weak base, I've got those videos out there for you, as well as chemical equilibrium. Alright, good luck chemists, and hopefully you'll come back again and see my videos, make a comment, like, subscribe, that would be wonderful.
Nag-gets po ba? Taas ang kamay na nakaget sa video. Lahat nakaget ng video. So yun lang naman, kung ano yung discuss natin, nagbigay lang din sa lang examples. No? Oo, kasi amphoteric or amphiprotic. Pero ang definitions na ganun din. Ang amphiprotic kasi, ang amphiprotic nakalagay doon, parang nilagyan siya na for some circumstances. Yun yung nilagyan ng ibang definition sa amphitronic. Pero, ang ibig sabihin nga ng amphitronic ay kapag nag-a-act siya, pwede siyang mag-act as acid or base. Nagbagay din naman yung amphitronic. Kaya nilagyan siya ng ilalim na open parenthesis. Okay? So, sana malinaw, no? Ang bronzidoric acid, lagi siyang may kakambal na conjugate base. No? Kung iisipin natin, bakit sasabihin mo, ma'am, bakit kung siya ay bronzidoric base, bakit hindi conjugate base ang ilalagay? Kasi kung titignan natin, for example, katulad dito, bronzidoric acid siya, HCl. Tapos, ang kapartner niya, dito, kung titignan natin, ay yung Cl na lang, di ba? Katulad yung nilagay kanina, may colon, tapos magiging Cl na lang siya. So, kung ito ang acid natin, ito ang magiging conjugate base. Bakit ba tinawag na conjugate? Ano sabi? Bakit tinatawag na conjugate? Kapag yung dalawa ay ang difference lang nila ay isang proton or yung H. Diba? Isa lang yung difference nila kaya tinawag na conjugate. Katulad din nitong base, ang partner niya conjugate acid. NH3 and NH4, ang difference ng nila ay isang H. Okay? Kaya siya tinawag na conjugate. And then, kung makikita natin, di ba kapag nagdodonate, siya ay acid. So ngayon, kapag ito ay nag-donate nga doon, sa iba, magiging bronzidoric base. Pero pag tinignan niyo ito, yung conjugate base, di ba kailangan siya ay mag-a-accept ng H para mabalik ulit siya dito. Yun yung ibig sabihin mo. Parang babalik ka rin yung equation. Ito ay nagbigay. Ngayon, ito naman, tatanggap para maibalik ulit siya sa HCl. So, katulad nito, ito ay tumanggap. Diba, ng H. Pero, baliktad. Itong NH4, pag binaliktad mo lang yung equation kung ito yung NH4, kailangan niya na magbigay. Para maibalik siya sa NH3. Para mabawasan ulit siya ng isa. Diba? Kailangan niya magbigay para mabalik siya sa NH3. Kasi binabaliktad natin yung equation regarding dun sa conjugate na term. Okay? So, kaya siya tinatawag na conjugate acid. Kasi kailangan niya magbigay. Kapag nandito siya sa product side. Okay? So, hindi natin lalagyan ng conjugate na word kung ang definitions natin ay manggagaling dito sa reactants. Tama? It's either bronzidoric acid lang at bronzidoric base. Okay? So, kung clear na po yan, proceed na tayo sa pH. Computation ng pH. Madali lang naman ang pH.
This may come as a bit of a shock to you, but I'm not super into personal grooming. Like, I understand soap and shampoo, but there's all this other stuff now, and I keep seeing references to pH balance everywhere. pH balanced soaps and shampoos and deodorant and makeup abound in supermarkets and drugstores. I've even seen pH balanced water. We talked a lot about balance over the last couple of weeks, and pH balance is related to the equilibrium state of a reversible reaction. You're also probably familiar with the pH scale, and you know that it has to do with acids and bases. But what is pH exactly, and why is it weirdly written with a lowercase p and a capital H? And also, what about pH's alter ego, pOH? The capitalization thing is probably the easiest to answer because there is no answer. No one really knows what the P means. The Danish chemist who came up with the term, a guy with the absolutely amazing name Sørensen, never explained his reasoning. Some people think that it comes from some form of the word power, whether it's puissance in French or maybe Latin pondness. Probably this came from the common habit chemists have of differentiating a test solution labeled P from a reference solution called Q. But thinking of the B as standing for power does help us remember the meaning more easily. The H part is even easier. It stands for hydrogen because hydrogen ions or protons are pivotal to the behavior of acids and bases, which is what pH describes. So you can think of pH as basically the power of hydrogen in the solution, the strength of the acid or base character of a substance. And it all revolves around one very important point of focus, our old friend water. just one more of the ways. We normally think of water as a perfectly neutral substance, neither acidic nor basic, and that's true. But, as I've mentioned before, water can also function as an acid, releasing hydrogen ions, also known as protons, and as a base, consuming them. How on earth is that possible? In order to explain, we first have to understand what the pH of the substance really tells us. Well, chemically, we say that pH represents the power of hydrogen in a solution. It's mathematically defined as the negative of the base 10 logarithm of the concentration of hydrogen ions in solution. Okay, so now that you're terrified, I'm here to help. So yeah, logarithms can seem a little bit scary at first, but the ones that we're using here are super easy. And bonus, once you get familiar with them here, it'll be that much easier to understand in math class. So now that we have the scary mathematical definition, let's do the simplest mathematical definition. At any given moment, there will be a certain number of hydrogen ions in solution. A very small number. The concentration will be a number like 1 times 10 to the negative 50 moles per liter. That negative 5 is your base 10 logarithm. Take the negative of that and you get the pH, 5. Now let's get a bit more into the weeds. Logarithm, or log, of a number is the exponent to which another number called the base must be raised to produce the target number. So for base 10 logs, the base is 10. They're what we use most in chemistry, and they're really easy to understand, and also what we base scientific notation on. So as an example, the base 10 logarithm of 100 is 2, because 10 raised to the power of 2, or 10 squared, equals 100. Base 10 logs are so common that we often leave the subscript 10 off when we write it. Like your calculator has a log button, that's just for base 10 logs. So what in the name of CERN said does this have to do with base melting acids? Well, I'm getting to that, and it all starts with water's crazy potential to act as both an acid and a base. Random changes in the tiny electrical fields around the atoms in water occasionally cause the molecule to break apart. Specifically, a hydrogen ion, or proton, will break off from one molecule and attach itself to another one, forming a hydronium ion, H3O+, and a hydroxide ion, OH-. This is why water can act as both an acid and a base. Its molecules can both release and accept protons. In this case, it's only interacting with itself, but water can interact in the same way with other acids and bases. Sometimes you see the hydronium ion written as a simple hydrogen ion, H+, allowing the reaction to be written with only one water molecule. It's not technically accurate, but it's close enough to reality that it can be used to simplify things. So, when we say that the pH is the negative log of the hydrogen ion concentration, yeah, we actually mean hydronium ion concentration. Just another thing that early scientists got a little bit wrong, now we have to live with. Anyway, this dissociation of water is a reversible reaction, and in fact, the ions always reform into water within a tiny fraction of a second. But it's happening all the time, constantly, in your body's water, in the water inside your cells, in the ocean, always. However, at any given instant, only a tiny number of molecules are dissociated into ions. In fact, the exact number of these molecules is well known to chemists. It's the equilibrium constant for this reaction, and because it's such a special reaction, it has its own name, the water dissociation constant, or Kw. Kw is equal to 1.0 times 10 to the negative 14. The formula for Kw is solved like any equilibrium constant, concentrations of products over concentrations of reactants, all raised to the exponents based on the coefficients of the balanced reaction. There is, however, one difference. Because the ions represent such a tiny proportion of the total mass, the water itself is essentially pure. And pure substances, because they don't have concentrations, aren't included in equilibrium calculations. So the formula for Kw becomes simply the hydronium ion concentration times the hydroxide concentration. According to the balanced equation for the dissociation of water, hydronium and hydroxide are formed in a 1-to-1 ratio, so their equilibrium concentrations must be equal. That means we can call the concentration of H3O+, for example, X, then the concentration of OH- must equal X as well. So the formula for the dissociation constant, 1.0 times 10 to the negative 14, simplifies even further to X times X, or X squared. Suddenly, it's crazy easy. The equilibrium concentration of each ion is just the square root of 1.0 times 10 to the negative 14. Tough monkey on the old calculator in hello, both concentrations equal 1.0 times 10 to the negative 7 moles per liter of equilibrium. The pH then is simply the negative log of that, which is 7. This, my friends, is the basis of the pH scale. Water is neutral, so 7 is the center of the scale. And I can prove it too. This is a strip of paper that's been infused with a chemical called litmus. Litmus is a pH indicator, a chemical that turns different colors at different pHs. There are many different indicators with many different colors, but we'll talk more about those next week. For now, just know that litmus paper turns pink in in acids, blue in bases, and a sort of light purple when it's neutral. But one thing you need to remember about the pH scale, because pH is calculated from a negative logarithm, it turns everything backward. When the hydrogen ion concentration goes up, the pH gets lower. For instance, if a little acid, such as vinegar, were added to water, the concentration of hydronium ion might rise to, say, 1.0 times 10 to the negative 4th moles per liter, which is 1,000 times more than before. That concentration would push the pH down to 4. On the other hand, the base, such as ammonia, would consume a lot of hydrogen ions if it were added to water. If the hydrogen ion concentration drops to 1.0 times 10 to the negative 11, 1,000th of the equilibrium concentration, the pH would be 11. As you can see, the logs turn out to be a mathematical shorthand that saves us from dealing with very huge or very tiny numbers. The pH scale then is normally written from 0 to 14, with numbers below 7 representing acids and numbers above 7 representing bases. It can also go below 0 or above 14, but that only happens in super extreme cases that you are very unlikely to encounter, at least I hope. Acids like hydrochloric or nitric acid, which ionize strongly, sometimes even completely, thus releasing a lot of protons, are called strong acids because they raise the hydrogen concentration a lot. They also generally have very low pHs. Weak acids like citric acid dissociate incompletely, releasing much smaller amounts of hydrogen ion, and therefore they usually have higher pHs, generally considered to be in the 4 to 6 range. Strong bases, meanwhile, like sodium hydroxide, consume large amounts of hydrogen ions, leaving the concentration very low, so they tend to have very high pHs. Weak bases, like sodium bicarbonate, baking soda, consume much less and generally have pHs in the 8 to 11 range. Neutral pH is technically just 7.0, but in a more practical sense, it's usually considered to be between 6 and 8. So if pH is based on the concentration of hydrogen, that is hydronium ions, what about the concentration of hydroxide ions? Just as we can calculate the pH of a substance from its hydrogen ion concentration, we can calculate the pOH, the negative log of the hydroxide concentration. This is easy because Kw never changes. Although the concentrations of hydrogen and hydroxide are only equal in pure water or perfectly neutral solutions, the product of the two concentrations always equals 1.0 times 10 to the negative 14 in any aqueous solution. So like orange juice, which is really just an aqueous solution of sugar and citric acid and a few other things. Say the hydrogen ion concentration in your OJ is 3.2 times 10 to the negative 4 moles per liter. Just for the fun of it, let's go ahead and calculate what the pH is at that point, which turns out to be 3.5. But we can also use the Kw and the hydronium ion concentrations to do a very simple division problem to find the hydroxide concentration. It works out to 3.1 times 10 to the negative 11 moles per liter. Once we have the concentration, we can take another step. We can find the pOH of the solution, which is similar to the pH, simply the negative log of the OH concentration. The pOH, in this case, is 10.5. And now for a tip that's just more awesome and cooler than an ice cream corn dog, the sum of the pH and the pOH is always 14. In the example we just did, pH was 5.4, the pOH was 8.6. And yeah, you add those together, 14! Surprise! Okay, maybe that's only cool to me, but that's never stopped me before. I love this stuff. And next week I hope to really bend your mind by showing you how to make the pH of the solution hold steady even if you dump a strong acid or base in it. In the meantime, thank you for watching this episode of Crash Course Chemistry. If you paid attention, you learned how pure water ionizes to form hydronium and hydroxide ions in reversible reactions, and you learned about the equilibrium constant for that reaction, which has a special name, the water dissociation constant. You learned some examples of acids and bases and neutral substances, as well as why some acids and bases are called strong and others are called weak. You learned about logarithms and how you can use them to calculate the pH of the substance, and a little bit about pOH, which can be calculated with logarithms, also with subtraction. And finally, you learned about some cool mathematical connections between pH and pOH. This episode was written by Andy Gonzalez and edited by Blake D. Pastino. The chemistry consultant was Dr. Michael Langner. It was filmed, edited, and directed by Nicholas Jenkins. The script supervisor was Catherine Green. Michael Ronda is our sound designer, and our graphics team is Dog Cafe.
Okay, so dito na lang sa video, no, very clear yung discussion. It is about the computation of pH. No? Ang formula natin for pH, ano nga ulit ang pH power of hydrogen. Okay, baka natin yung compute para malaman natin kung yung ating bang solution is acidic or basic. No? pH is negative log of H plus. Okay? pOH is equal to negative log ng OH. So, napakadali naman na tandaan, no? Kapag kinuha mo yung power ng hydrogen, H plus. Okay? Pag hydroxide naman, edi OH minus. Tapos, ano pa yung pinaka-last? pH plus POH should be always equal to 40. Okay? Bakit po 40 yan? Dahil meron tayong scale. Tama? Meron tayong pH scale. Scale na. Okay? Scale na namin. Ito yung 7. Tapos, ito ay 0 to 40. Okay? Kapag nandito ka daw, pag ang pH mo ay nandito, ay active. Okay? Tapos, pag 7 to 14, ang pH mo, ang value ng pH mo ay 7 to 14, ito ay base. Okay? So, kapag sa computation mo, lumabas na 1, kasi acid siya. Kapag ang lumabas na pH mo ay 13, siya ay base. Okay? Tapos, pag 0, siya yung strongest acid, at kapag 14, siya ang strongest base. Okay? Kung makikita nyo dun sa video, isend ko din yung link sa ating GC kasi parang sa mga modular class, no? Makikita nyo yung, or pwede na kayo mag-search sa Google ng pH scale na nandun yung list ng mga substances, no? Kunwari, yung na-extract mo na lemon juice, saan siya? Siyempre, acid yun. Pero kung ano yung typical na scale niya, kung nasa 2, kung nasa 3, tapos yung mga bleach na ginagamit sa buhok, siya ay strongest, consider siya as strongest base. No? Kahit kasi base, parang feeling kasi natin kapag acid, lagi yung nakakasunod ng balat, no? Pero meron din kasi kapag naging strong base siya, pwede din siya makasunod ng balat. No? Hindi lahat ng kasabi kong acid ay yun lang yung nakakasunod ng balat. Okay? Tapos, pinili naman din yung tawag dito, equation kung paano mo matatransform ang isang logarithm sa exponential form, no? Yung log daw natin na nakikita sa column U, ang default na base niya is base 10. Okay? Kasi sa calculus nyo, meron doon na ganito talaga yung log, tapos meron square, tapos meron yung square, ganyan. Diba? May ganito part sa calculus. Ito kasi, sige, pwede mo maiba yung base. Pwede siya mag-use, ano ba ang mga base namin sa logarithm? Pwede 2, pwede tayo may base 8, may base 10 at base 16. Yung mga base natin, no? Okay. So, last na natin ay ito. Henderson, ito ay under ng week 4. Kung makikita niyo, no? Napaka-unti lang ng discussion sa week 4. Mas marami pa yung activity na pinapagawa.
This may come as a bit of a shock to you, but I'm not super.
Ito ay Henderson-Hazelbach equation.
Hello, and welcome to Chemistry with Dr. T. I'm Dr. T, and today I will be presenting a short lesson on the Henderson-Hasselbalch equation. So what is the Henderson-Hasselbalch equation? It is an equation that is used to quickly calculate the pH of a buffer solution. A buffer solution is a solution that contains a weak conjugate acid-base pair that is able to accommodate the addition of strong acids and bases without the pH of the solution changing much. It is based on some underlying assumptions that I'll get to later in the video. And its main advantage is that the concentrations of the buffer components can be used directly in the equation rather than having to use an ICE chart. However, I always recommend that we write the chemical equilibrium equation to make the problems easy to solve. The derivation is in your textbook or class lectures. So, what is it used for? As I mentioned before, the Henderson-Hasselbalch equation is used to quickly calculate the pH of a buffer solution. In the real world, biologists, biochemists, and chemists all use the equation to calculate the pH of various buffers for various experiments. Students also use the Henderson-Hasselbalch equation to calculate the pH of buffer solutions for laboratory experiments as well as for exam problems. The Henderson-Hasselbalch equation is shown in the bottom here. It states that the pH of a buffer solution is equal to the pKa of the conjugate acid plus the log of the concentration of the conjugate base divided by the concentration of the conjugate acid. So how is it used? I give an example problem here that 0.20 moles of benzoic acid and 0.10 moles of its conjugate base, sodium benzoate, are dissolved in 1 liter of pure water. What is the pH of this buffer solution? Given is the Ka of benzoic acid, which is 6.3 times 10 to the minus 5. This is normally found in your textbook or some other reference source. So, how do we use the Henderson-Hasselbalch equation? Well, first, as I mentioned before, I always recommend that we go ahead and write the chemical equilibrium equation first. So we'll represent the acid with HA. And this is in equilibrium with H plus and A minus conjugate base. These are all aqueous, of course. And what this shows is that a small amount of this weak acid in solution will dissociate into H plus, which gives the acidity of the solution, and its conjugate base A minus. So we'll just write an ion rate on the C chart. And you start with 0.20 moles of benzoic acid in 1 liter of pure water, so that calculates conveniently to 0.20 molar. You start with 0 H plus and 0.10 molar in the conjugate base, sodium benzoate. So from here, we need the pK. I gave you the Ka, but this is easily calculated in much the same way that the pH is calculated. The pKa is equal to the negative log of the Ka. And using 6.3 times 10 to the minus 5 here, we get that the pKa is equal to 4.202. Now, from here, we just plug our numbers into the equation. So pH is equal to the pKa, 4.202, plus the log of the concentration of the conjugate base, which is 0.10 molar. We get this from the I of the ICE term. And this will be divided by 0.20 molar. The molars cancel out. And what this brings us to is pH is equal to 4.202 plus negative 0.301. And this will give us the final answer. pH is equal to 3.901, which rounds to 3.9. And that is it. That is how simple the Henderson-Hasselbalch equation makes it to calculate the pH of a buffer solution. Now I'd like to run through a few pieces of information that will help you understand the Henderson-Hasselbalch equation better, as well as to use it the most effectively. So the central assumption made by the Henderson-Hasselbalch equation is that the amount of acid that ionizes in solution is negligible compared to the amount of acid and conjugate base that are used to form the buffer. So what does this mean for you? This means that the Henderson-Hasselbalch equation is inappropriate to calculate the pH of a solution containing only a strong acid or strong base. For that, you would use that the pH is equal to the negative log of the concentration of H plus solution. So you need to be sure that the amount of acid acid and conjugate base that are added are at least about 100 times larger than the Ka. So in our case, the Ka is 6.3 times 10 to the minus 5. So that means that you would want to add at least about 10 to the minus 3 moles of the conjugate acid base K in order for the assumption made by the Pearson-Hasselbalch equation to not be violated. I'd also like to tell you a little bit about the pH and buffer capacity. The pH of a buffer solution is determined solely by the Ka of the conjugate acid. The amount of acid or base that can be added, or the amount of strong acid or strong base that can be added to the system and neutralized by the buffer before the pH starts to change by a significant amount depends on the amount of conjugate acid and conjugate base used to make the buffer. This is known as the buffer capacity. So, for example, a solution that is 1 molar in benzoic acid and 1 molar in sodium benzoate will have the same pH as a solution that contains 0.1 molar in benzoic acid and 0.1 molar in sodium benzoate. However, the 1 molar solution has a much larger buffer capacity and it can therefore neutralize a much greater amount of added strong acid or strong base. And with that, I would like to thank you for watching this short lesson on the Pearson-Hasselbalch equation. For more resources, please visit my website, www.chemistrywithdrt.com. That's chemistrywithdrt.com. Thank you.
So ito po ay under ng before, no? Yung Henderson and Hasselbalch equation. Equation ulit natin dyan. pH, ito kasi A for buffer solution, no? pH, pKa, nilista niyo ba? Plus log ng conjugate base over conjugate acid. Okay, yun ang equation niya. Paano daw natin masasabi na buffer solution? Ang buffer solution daw ay merong weak pair na conjugate acid and base na kung saan kapag yung solution na yun, dinagdagan mo ng very strong acid or very strong base, hindi gaano mag-change ng pH. Okay, nakikita natin po ang ibig sabihin ng buffer solution. Kaya parang yung buff na word ay hindi agad mag-change, no? Parang pipigilan niya muna. Yun yung buffer